Welcome to this comprehensive lecture on the Indian monsoons. Today, we are going to dive deep into one of the most fascinating and impactful weather systems on Earth. We'll explore what monsoons are, the factors that drive them, and the classical and modern theories that explain their mechanisms. Let's get started.
The term monsoon actually originates from the Arabic word mausin or the Malayan word monsin, both of which simply mean season. But in meteorology, a monsoon is much more than just a season. It refers to periodic or secondary winds that completely reverse their direction as the seasons change. You can think of them as land and sea breezes, or convection cells, but operating on a massive continental scale.
The monsoon is fundamentally a double system of seasonal winds. During the summer, we experience the southwest monsoon winds, which flow from the sea to the land, bringing abundant moisture. Then, as winter approaches, the system reverses. The northeast monsoon winds take over, flowing from the land back out to the sea, bringing much drier conditions to most of the subcontinent.
While we often associate monsoons exclusively with India, they are actually found in several parts of the world. They are peculiar to the Indian subcontinent, Southeast Asia, and parts of Central Western Africa. However, they are by far the most pronounced and dramatic in the Indian subcontinent. Other areas, like northern Australia and parts of Africa, also experience these seasonal shifts in wind patterns and precipitation, but the Indian monsoon remains the classic example.
The direction of these winds dictates when different regions get their rain. Countries like India, Indonesia, Bangladesh, and Myanmar receive the vast majority of their annual rainfall during the southwest monsoon season in the summer. Conversely, regions like Southeast China and Japan get their primary rainfall during the northeast monsoon season. In India specifically, while the southwest monsoon drenches most of the country, the retreating northeast monsoon is responsible for bringing crucial winter rainfall to the southeastern coast, particularly Tamil Nadu and southern Andhra Pradesh.
What drives this massive reversal of winds? It all comes down to atmospheric pressure. The southwest monsoons are formed due to intense heating that creates a massive low-pressure system over the Tibetan Plateau in the summer. Nature abhors a vacuum, so moist air from the ocean rushes in to fill it. In winter, the opposite happens. Intense cold creates high-pressure cells over the Tibetan and Siberian plateaus, pushing dry air outward towards the ocean, creating the northeast monsoons.
Let's look at a question from the 2014 UPSC exam. The seasonal reversal of winds is the typical characteristic of which climate? The options are equatorial, Mediterranean, monsoon, or all of the above. Based on what we just discussed, the answer is clearly C, the monsoon climate. This seasonal reversal is the defining feature of the monsoon, dictating the stark contrast between the wet and dry seasons.
Now let's break down the specific factors responsible for the southwest monsoon. The foundational setup requires two main components. First, the intense heating of the Tibetan Plateau during the summer months, which creates a strong thermal low-pressure zone. Second, there is a permanent high-pressure cell known as the Mascarene High, located in the South Indian Ocean, near Madagascar. The pressure gradient between this high in the south and the low in the north is the primary engine of the monsoon winds.
Having the pressure difference isn't enough to start the rain. Several factors influence the actual onset or arrival of the southwest monsoon. Along with the Tibetan low and the Mascarene high, the timing is heavily controlled by upper air circulation, specifically the northward shift of the subtropical jet stream, the formation of the tropical easterly jet, and the northward migration of the intertropical convergence zone, or ITCZ. We will explore exactly how these mechanisms interact shortly.
Once the monsoon has arrived, what determines if it will be a year of heavy floods or severe droughts? The intensity of the rainfall depends on several dynamic factors. The absolute strength of the pressure difference between Tibet and the Indian Ocean is crucial. Additionally, regional phenomena like the Somali jet, a low-level wind, and the Somali ocean current play major roles in transporting moisture. Furthermore, broader climatic patterns like the Indian Ocean branch of the Walker Cell and the Indian Ocean dipole can significantly enhance or suppress monsoon rainfall. As we move into winter, the system flips to create the northeast monsoon. This is driven by the rapid cooling of the Asian landmass, which forms massive high-pressure cells over the Tibetan and Siberian plateaus. At the same time, the Mascarene High in the southern hemisphere migrates westward and weakens. Finally, the ITCZ, which tracks the sun, moves south of India. This combination pulls the dry, cold air from the continent out over the ocean.
Here's another UPSC question, this one from 1996. High temperature and low pressure over the Indian subcontinent during summer draws air from the Indian Ocean, leading to the inblowing of the... The correct answer is B, the southwest monsoon. The intense low pressure acts like a vacuum. As the air is drawn in from the southern hemisphere across the equator, the Earth's rotation, specifically the Coriolis effect, deflects these winds to the right, causing them to approach India from a southwesterly direction.
Let's look at a fascinating regional aspect of the monsoon that was featured in the 2023 UPSC exam, the Purvaiya. In the Bhojpur region, which spans parts of Bihar and Uttar Pradesh, the southwest monsoon is actually known as the Purvaiya, which translates to easterly. The timely arrival of the Purvaiya is absolutely critical for the local economy, as it provides the essential rainfall needed for water-intensive agricultural activities, particularly the cultivation of paddy. But wait, if it's the southwest monsoon, why call it an easterly wind? There are two reasons. Geographically, as the monsoon winds travel northeast up the Bay of Bengal, they hit the massive barriers of the Himalayas and the Meghalaya Plateau. These mountains deflect the winds westward, up the Ganga Plain. So by the time these winds reach the Bhojpur region, they are actually blowing in from the east. Linguistically, the word Purvai simply means east in the local Bhojpur language, leading to the name Purvaiya.
The Purvaiya isn't just a weather event, it deeply influences the cultural ethos of the region. Culturally, major festivals like Chhath Puja are tied to the agricultural cycles dictated by these rains. The humid weather even changes the local cuisine, prompting a shift toward foods like dahi chura and pakoras. In folklore and literature, the Purvaiya is frequently personified in songs and stories as a harbinger of hope and prosperity. It is a beautiful example of how environmental factors shape human culture.
Now that we understand the impacts, let's look at the mechanisms. How exactly do these monsoons form? The truth is, the complete origin is incredibly complex and still being researched. Historically, Arab traders were the first to study these winds scientifically, as their livelihoods depended on using these seasonal winds to sail to India. As early as the 10th century, the Arab explorer al-Masudi provided detailed accounts of how the ocean currents and winds completely reversed over the North Indian Ocean.
Fast forward to the 17th century, and we get the first formal scientific theory from Sir Edmund Halley, the same scientist famous for Halley's Comet. Halley proposed a thermal concept. He argued that monsoons are simply the result of thermal contrasts between continents and oceans, caused by the fact that land heats up and cools down much faster than water. In his view, the Indian monsoon was just a giant version of the daily land and sea breezes you feel at the beach. According to Halley, during the summer, the sun's apparent path moves north to sit vertically over the Tropic of Cancer. This bakes the Asian continent, creating high temperatures and a massive low-pressure zone over Central Asia. Meanwhile, the oceans, the Arabian Sea and Bay of Bengal, remain relatively cooler, maintaining higher pressure. This pressure gradient forces moist air from the sea to flow onto the land, creating the summer monsoon rains.
In the winter, the mechanism reverses. The sun moves south over the Tropic of Capricorn. The massive landmass of northwestern India cools down rapidly, becoming much colder than the surrounding Arabian Sea and Bay of Bengal. This creates a high-pressure zone over the land and relatively lower pressure over the water. Consequently, the winds reverse direction, flowing from the dry land out to the sea, resulting in the winter monsoon.
Halley's theory makes logical sense, but it has significant drawbacks. If differential heating were the only factor, we should see identical monsoons everywhere on Earth where large land masses meet oceans, but we don't. Furthermore, a simple thermal model cannot explain the complex intricacies of the Indian monsoon, such as why it suddenly bursts over the Kerala coast, or why its arrival is sometimes delayed by weeks. Because of these gaps, Halley's theory lost relevance as we discovered more complex atmospheric dynamics.
To truly understand the monsoon, we must look to modern theories. While differential heating is still recognized as the foundational engine, modern meteorology incorporates several other critical factors. The unique shape of the Indian subcontinent, the orography, meaning the placement of massive mountain ranges like the Himalayas, and most importantly, the complex air circulation patterns high up in the upper troposphere, specifically the jet streams. Let's look at how these factors create a seasonal rhythm. Let's trace the seasonal rhythm starting in spring, from March to May. As summer approaches, solar heating increases over the subcontinent and Tibet. However, a subtropical high-pressure belt sits firmly over northwest India. Crucially, high above the ground, the subtropical jet stream is blowing south of the Himalayas.
As long as this powerful jet stream remains in this southern position, it creates subsidence, sinking air, that completely blocks the monsoon cell from forming, inhibiting any summer rain.
Things begin to change dramatically between late May and early June. As the sun's apparent position moves north toward the Tropic of Cancer, the atmospheric belts shift with it. The ITCZ moves north over the Tibetan Plateau. Most importantly, the subtropical jet stream is forced to shift from the south of the Himalayas to the north of the Tibetan Plateau. This northward migration of the jet stream is the primary trigger associated with the onset of the Indian monsoon.
Once the subtropical jet stream moves out of the way in early June, the monsoon bursts onto the scene. A new upper air wind, the tropical easterly jet, forms over the Indian plains. This jet creates cyclonic, low-pressure conditions near the surface. With the high-pressure block removed, the monsoon cell develops in a matter of days. Moist air from the high-pressure Indian Ocean rushes violently toward the intense low-pressure void over Tibet, resulting in the sudden, dramatic onset of the southwest monsoon.
During the peak rainy season in July and August, the subtropical easterly jet fluctuates north and south, which causes the intensity of the rainfall to vary from place to place. The system is continuously fueled by warmth and moisture. A key player here is the Somali jet, a fast-moving, low-level jet stream that acts like a conveyor belt, scooping up massive amounts of moisture from the Indian Ocean and dumping it over the Indian landmass.
As we move into September and October, the season begins to wind down. The massive Tibetan Plateau starts to cool, losing its intense low-pressure vacuum. This cooling allows the subtropical jet stream to transition back to its winter position, south of the Himalayas. Simultaneously, the ITZZ shifts back towards the equator. Consequently, the subtropical high-pressure belt returns to the northern Indian plains, effectively shutting off the moisture supply and causing the monsoon rains to cease.
By November, the winter rhythm is fully established. An anticyclonic winter monsoon cell forms, characterized by heavy, sinking air masses over the subcontinent. This generates the northeast monsoon, relatively moisture-free winds that blow from the land out toward the sea. For most of India, this brings a period of settled, dry, and cool weather. But as we've seen, this is just one part of the story. Next, we will explore another crucial framework for understanding these dynamics, the air mass theory. Moving right into the mechanisms driving the Indian monsoon, let's look at the classical air mass theory. According to this model, the monsoon isn't some isolated phenomenon. It is simply a massive seasonal modification of the normal planetary winds found in the tropics. The entire system is driven by the seasonal migration of the intertropical convergence zone. Under this theory, the famous southwest monsoon winds that bring rain to India are actually just expanded equatorial westerlies that have pushed into the territory normally occupied by the trade winds. To understand the air mass theory, we have to understand the ITZZ, or the Intertropical Convergence Zone. Think of the ITZZ as a meteorological equator. It is the exact meeting place where the southeast trade winds from the southern hemisphere crash into the northeast trade winds from the northern hemisphere. When these two massive air masses collide, the air has nowhere to go but up. This creates a permanent region of ascending warm air, which leads to massive cloud formation and heavy, continuous rainfall.
The ITCZ is not stationary. It follows the sun. During the summer season, the sun shines vertically over the Tropic of Cancer, causing the ITCZ to shift dramatically northwards over the Indian landmass. Because the ITCZ has moved north, the southeast trade winds from the southern hemisphere are forced to cross the equator to reach it. As soon as they cross the equator, the Earth's rotation, specifically the Coriolis force, deflects them to the right. These deflected winds now blow from the southwest to the northeast, and we know them as the southwest monsoons.
When these newly formed southwest monsoons finally meet the existing northeast trade winds, they form what is known as the monsoon front. By July, the ITCZ has shifted all the way up to 20 to 25 degrees north latitude, settling right over the Indo-Gangetic Plain. In this specific position, the ITCZ is often referred to as the monsoon trough. This trough acts like a giant vacuum, pulling in moisture-laden winds from both the Arabian Sea and the Bay of Bengal, resulting in a continuous series of thunderstorms and maximum rainfall over the subcontinent. Because the ITCZ swings back and forth across the equator like a pendulum, meteorologists categorize it by its seasonal location. When it shifts north in July, it is called the Northern Intertropical Convergence Zone, or NITCZ. This is the zone of heavy clouds that brings India its rainy season.
Conversely, in January, it swings south of the equator, becoming the Southern Intertropical Convergence Zone, or SITCZ. When the convergence zone is down south, India experiences its dry winter season.
While the air mass theory explains the surface winds, the latest and most comprehensive explanation is the jet stream theory. To truly understand the monsoon, we have to look high up into the atmosphere. Jet streams are narrow bands of incredibly fast-moving air. They don't flow in straight lines, they meander in giant waves. The peaks of these waves, where warm air pushes north, are called ridges. The dips, where cold air plunges south, are called troughs. These high-altitude waves dictate the weather on the ground.
Let's look at how a trough affects the surface. In the upper atmosphere, right at the trough of a jet stream, the winds rapidly diverge or spread apart. This spreading creates a void or lower pressure high up in the atmosphere. To fill this void, air from the Earth's surface is rapidly sucked upward. This rising air creates a strong low-pressure system at the surface. Surrounding surface winds rush inward to fill the surface low, and the Coriolis effect spins them into a cyclonic rotation, leading to heavy storms and depressions.
The exact opposite happens under a jet stream ridge. High up in the atmosphere, the winds entering the ridge are rapidly converging, or piling up. All this accumulating air has to go somewhere, so it is forced violently downward toward the Earth's surface. This descending heavy air creates a massive high-pressure system on the ground. The air hits the surface and spreads outward, creating an anticyclonic rotation. This sinking air prevents any clouds from forming, resulting in very clear, dry weather. The specific jet stream that controls the Indian monsoon is the subtropical jet stream, or STJ. This is a fierce, narrow band of westerly winds flowing high in the upper troposphere, about 12 to 14 kilometers above the Earth, right between 25 and 35 degrees north latitude. The winds here are brutal, routinely blowing between 150 and 300 kilometers per hour, sometimes reaching 400. The sudden onset, or burst, of the Indian monsoon is entirely dependent on the behavior and positioning of this high-altitude river of air.
The subtropical jet stream migrates with the seasons, and this migration acts as the master switch for the monsoon. During the winter, the STJ flows south of the Himalayas, but as summer approaches, it shifts dramatically to the north. By early June, it moves to the northern edge of the Himalayas, and by July, it sits over the Tibetan Plateau. This northward jump is the very first indicator that the monsoon is about to begin. Conversely, when the STJ drops back south of the Himalayas later in the year, it signals the withdrawal of the monsoon.
Let's examine the STJ during the winter months. As it blasts across Asia, it encounters a massive obstacle, the Himalayan mountains and the Tibetan Plateau. This acts as both a physical wall and a thermal barrier, physically splitting the jet stream in two. The weaker northern branch flows above Tibet at about 70 to 90 kilometers per hour. The southern branch, however, is much stronger, roaring south of the Himalayas at roughly 240 kilometers per hour. These two branches eventually reunite far to the east, off the coast of China. As winter turns to summer in March, the STJ begins its northward march, and that oppressive southern branch starts to weaken. By the end of May, the southern jet completely breaks down and shifts entirely north of Tibet. This is the trigger for the monsoon burst. The high-pressure lid over northwest India is suddenly removed and shifts into Central Asia. Simultaneously, an easterly jet emerges over peninsular India. The entire atmospheric circulation reverses. Surface high pressure is replaced by a massive low-pressure system, which aggressively pulls in the southwest monsoon winds. You might wonder, if India is incredibly hot in April and May, creating strong surface low pressure, why doesn't the monsoon start then? It's a fascinating paradox. Even though the ground is baking and creating a surface vacuum, the upper atmosphere refuses to cooperate. The southern branch of the STJ is still stubbornly positioned south of the Himalayas during these months. The heavy, descending air from the STJ ridge acts like a physical lid, violently pushing down and obstructing the hot surface air from rising. Until that jet stream moves north, April and May remain completely dry.
The jet stream doesn't just control the timing of the monsoon. Its anomalies can cause catastrophic weather events, such as cloudbursts. A cloudburst is an intensely violent torrential downpour from a thunderstorm that lasts for a very short duration, sometimes just minutes. Because the volume of water is so massive and sudden, it almost always leads to deadly flash floods. Cloudbursts happen when a highly humid air mass gets physically trapped or stalled over a specific geographic location, forcing it to dump all its moisture at once.
A perfect example of this occurred in 2010. That year, a massive high-pressure system stalled over Russia, creating a historic heat wave. This static block of hot air acted like a boulder in a river, forcing the subtropical jet stream to meander wildly off its normal path. Because the jet stream was stalled, it couldn't transit across the Himalayas as it normally would. Consequently, the moisture-heavy monsoon cell pushing up from the Indian Ocean hit a dead end. Trapped with nowhere to go, it dumped catastrophic amounts of rain over Pakistan and the Himalayas, causing massive flooding. This shows how interconnected global wind systems are, which brings us to the broader influencing factors we will examine next.
Let us dive right into the atmospheric drivers of the monsoon, starting with the tropical easterly jet, or TEJ. In the lower troposphere, we have major high-velocity winds known as low-level jets. In the tropics, the two most prominent are the Somali jet and the TEJ. The TEJ is a dominant feature of the northern hemispheric summer, flowing between 5 and 20 degrees north latitude. It is remarkably persistent from June through early October, playing a massive role in our weather systems.
How does the TEJ form, and what does it do? While its exact mechanics are still being studied, we know it is triggered by the intense summer heating of the Tibetan Plateau. As soon as the subtropical jet shifts north of the Himalayas in early June, the TEJ quickly establishes itself, flowing east to west. This formation is critical because it reverses the upper air circulation, switching high pressure to low pressure, which effectively kickstarts the southwest monsoon. It even descends all the way near Madagascar to strengthen the high-pressure cell there. The Tibetan Plateau is an enormous block of highland that acts as both a mechanical barrier and a high-level heat source. During the summer, this massive plateau gets baked by the sun, becoming 2 to 3 degrees Celsius warmer than the surrounding air. Because it acts as a massive radiator in the middle of the troposphere, it heats the air above it, causing that air to rise. This rising air, or convergence, creates an intense low-pressure cell right over Tibet. This rising air over Tibet sets off a massive atmospheric circulation, known as the monsoon cell. As the air ascends, it hits the upper troposphere and spreads outwards. This is divergence. It travels south and gradually sinks or subsides over the equatorial part of the Indian Ocean. This sinking air builds up high pressure over the ocean, which then sweeps back toward the west coast of India as a return current. These equatorial westerlies pick up massive amounts of moisture from the ocean, eventually dumping it as rainfall over India. When winter arrives, the scenario completely flips. The Tibetan Plateau cools down very rapidly. The rising cyclonic conditions of summer cease, and the cold, dense air begins to sink, establishing a strong anticyclonic high-pressure cell. This massive high-pressure zone pushes air outward and southward, which significantly strengthens the northeast monsoons that blow across India during the winter months.
Recent observations show just how sensitive the monsoon is to Tibet's conditions. If the plateau stays hot for a long time, the tropical easterly jet strengthens, bringing heavy rain to India. However, if there is thick, widespread snow over Tibet that doesn't melt quickly, the plateau cannot heat up. Without that heat, the TEJ doesn't form properly, leading to weak monsoons and drought. Additionally, the physical bulk of the plateau is responsible for pushing the subtropical jet north in June and splitting it into two branches when it returns in October.
Now let's look at another crucial low-level jet, the Somali jet. This jet acts as a massive accelerator for the southwest monsoon. It originates near Mauritius and Madagascar, flows toward the coast of Kenya, and then shoots across the Arabian Sea toward India. By strengthening the permanent high-pressure zone near Madagascar, the Somali jet acts like a slingshot, driving the moisture-laden southwest monsoon winds toward the Indian subcontinent with incredible pace and intensity.
The winds of the Somali jet are so strong that they actually drag the ocean surface along with them, creating the fine later current in the Arabian Sea. Because it is driven by monsoon winds, this current actually reverses direction when the monsoon reverses. During the southwest monsoon, it pulls surface water away from the Horn of Africa, causing cold, nutrient-rich water to rise from the deep. While this coastal upwelling is fantastic for the local fishing industry, the zone is too small to have a significant impact on the Indian monsoon itself. A phenomenon that does have a massive impact on the monsoon is the Indian Ocean Dipole, or IOD. Discovered relatively recently, the IOD is a sea surface temperature anomaly. Think of it as a seesaw of water temperatures between two poles, a western pole in the Arabian Sea and an eastern pole south of Indonesia.
This temperature difference begins to develop around April or May and reaches its peak in October, heavily influencing where rain will fall. When the IOD is in its positive phase, it is excellent news for the Indian monsoon. During a positive IOD, winds push warm surface water from east to west. This makes the Arabian Sea unusually warm, while the waters around Indonesia become cooler. Because the water near India is warmer, there is significantly more evaporation. More evaporation means more moisture in the air, which translates to heavier, more reliable rainfall for the Indian subcontinent.
Conversely, during a negative IOD year, the seesaw tilts the other way. The warm water is pushed toward Indonesia, making that region much warmer and rainier. Meanwhile, the Arabian Sea becomes cooler than normal. Cooler water means less evaporation off the coast of India, which starves the monsoon winds of the moisture they need, often leading to deficit rainfall and drought conditions in India.
Just as El Niño has an atmospheric component called the Southern Oscillation, the Indian Ocean Dipole has an atmospheric counterpart called Equinu, the Equatorial Indian Ocean Oscillation. This refers to the shifting of atmospheric pressure cells between the Bay of Bengal and the Arabian Sea. During a positive equinu, the warm waters near the African coast lead to enhanced rising air and cloud formation there, while sinking air suppresses cloud activity over near Sumatra.
The interaction between these global systems is fascinating, and it's a frequent topic in advanced exams. The IOD often acts as a moderator for El Niño. El Niño typically suppresses the Indian monsoon, but if a positive IOD occurs at the same time, the extra moisture from the warm Arabian Sea can compensate for the El Niño deficit, as we saw in 2019. Furthermore, while El Niño can trigger an IOD event, the IOD can also develop entirely independently based on local Indian Ocean circulations.
Let's zoom out and look at the defining characteristics of the Indian monsoon. The word monsoon literally means a seasonal reversal of winds. From June to September, we have the southwest monsoon, bringing moist ocean air. After September, the winds flip, bringing the dry northeast monsoon. The second key characteristic is extreme variability. The monsoon is not a uniform blanket of rain. It varies wildly across space and time, bringing floods to some regions, while states like Rajasthan and Gujarat might simultaneously face arid, drought-like conditions.
To make sense of this variability, the India Meteorological Department uses a benchmark called the Long Period Average, or LPA. This is the average rainfall the country received during the southwest monsoon over a 50-year period, specifically from 1951 to 2000. The current LPA is 89 centimeters. The IMD grades the monsoon against this number. If rainfall is between 96 and 104% of the LPA, it's a normal monsoon. Drop below 90% and the country faces a deficient monsoon.
Spatially, the distribution of this rain is highly uneven. Regions like the Western Ghats and Northeast India, particularly Meghalaya, receive massive amounts of rain, up to 400 centimeters, largely due to orographic uplift, where mountains force moist air upward, causing heavy precipitation. Central India and the Gangetic Plains receive moderate rainfall. Meanwhile, regions shielded from these moisture-laden winds, like western Rajasthan and the high-altitude desert of Ladakh, receive very low rainfall, sometimes less than 100 millimeters.
During the monsoon season, you might experience a period where the rain suddenly stops for days or weeks. This is called a monsoon break. Normally, an elongated low-pressure area called the monsoon trough sits over central India, drawing in rain. But sometimes this trough migrates northward to the foothills of the Himalayas. When this happens, the Himalayan states get torrential rain, but rainfall over the rest of India, especially the core monsoon zone from Gujarat to Odisha, is severely suppressed or completely interrupted.
What causes these devastating monsoon breaks? Several global factors can pull the plug on India's rainfall. An El Niño event or a negative Indian Ocean dipole can weaken the overall monsoon circulation. Sometimes a cyclone forms in the Arabian Sea and moves west toward Yemen. This literally sucks the moisture away from the Indian subcontinent. Additionally, a suppressed phase of the Madden-Julian oscillation, a traveling band of tropical thunderstorms, can also stall the monsoon winds.
Because the monsoon is influenced by so many different global phenomena, it is arguably the most complex weather system in the world to predict. Forecasters aren't just looking at local temperatures. They have to monitor the Pacific Ocean for El Niño, the Indian Ocean for the IOD, the upper atmosphere for jet streams, the Atlantic Ocean, the Madden-Julian oscillation, and even the levels of pollution and desert dust in the air.
All these factors interact in chaotic ways. To give you an idea of how far-reaching these influences are, consider the Atlantic zonal mode, sometimes called the Atlantic Nino. Warming or cooling in the distant Atlantic Ocean generates eastward-moving atmospheric disturbances called Kelvin waves. These waves travel all the way through the troposphere to the tropical Indian Ocean, where they alter the atmospheric temperature. This changes the crucial temperature gradient between the ocean and the Indian landmass, directly impacting the strength of the monsoon.
So how does the IMD attempt to predict this? They issue forecasts ranging from immediate 24-hour nowcasts to seasonal long-range forecasts. Historically, the bedrock of long-range monsoon prediction has been the statistical model. This involves taking current climate parameters, like Eurasian snow cover or Pacific Ocean temperatures, and correlating them against 100 years of historical rainfall data to guess what will happen this year. However, because the climate is changing, historical statistics have often failed to predict major droughts.
Recognizing the flaws in purely statistical forecasting, the IMD introduced a digital dynamic system in 2015. Dynamic models use supercomputers to simulate the actual physics of the atmosphere in real time. The catch? These models require massive amounts of real-time data, and India currently lacks enough data collection centers to feed the models perfectly. While they still struggle with long-term seasonal monsoon predictions, these high-resolution models have become incredibly accurate for short-term, localized forecasts, helping warn farmers of impending extreme weather. The accuracy of these predictions is a matter of life and death for the economy, because the Indian monsoon is the lifeblood of its agriculture. The vast majority of India's farmland is rain-fed, meaning it lacks artificial irrigation. Adequate monsoon rains provide the exact soil moisture needed for water-intensive crops like rice, sugarcane, and cotton. When the monsoon fails, it triggers droughts and crop failures, devastating the livelihoods of millions of farmers and threatening national food security. Understanding the spatial progression of the monsoon is critical. The duration of the monsoon season actually decreases as you move from south to north. It hits Kerala in the south first, around early June, and takes over a month to reach the far north. When it retreats, it leaves the north first. Additionally, in the northern plains, the amount of rainfall decreases from east to west. As the moisture-laden winds travel inland from the Bay of Bengal across West Bengal and Bihar, they drop their rain, leaving much less moisture by the time they reach Haryana and Punjab.
We must also reiterate the profound impact of El Niño, a frequent subject of geographical study. When the central and eastern equatorial Pacific Ocean becomes unusually warm, it disrupts atmospheric circulation on a global scale. For India, these shifting wind patterns generally suppress the rising air needed for storm clouds, weakening the monsoon system and leading to significantly reduced rainfall over the subcontinent.
But it's not just natural global cycles at play anymore. Human activities are actively altering the monsoon. Large-scale deforestation, for instance in the Western Ghats, means fewer trees are transpiring moisture back into the air, which disrupts local rain recycling. Rapid urbanization in megacities like Mumbai create massive concrete heat islands that alter local winds and trigger extreme, concentrated rainfall. Even our farming practices, like massive over-irrigation in the Indo-Gangetic Plain, pump unnatural amounts of moisture into the air, disrupting regional weather patterns. Furthermore, industrial pollution is throwing a wrench into the system. High levels of aerosols and black carbon over northern India absorb solar radiation in the atmosphere, rather than letting it heat the ground. This messes with the temperature gradients needed to pull the monsoon winds inland, effectively weakening the flow. Add to this the overarching threat of global warming, which is heating the Indian Ocean and injecting more energy into the system, leading to highly erratic and extreme monsoon downpours. Despite these challenges, we must recognize that the monsoon climate successfully feeds over 50% of the global population residing in monsoon Asia. The seasonal reversal of winds provides a predictable, albeit variable, rhythm that traditional agriculture has adapted to over millennia. The heavy wet season replenishes aquifers, while the dry season allows for harvesting. This alternating cycle, combined with fertile soils, allows farmers to cultivate multiple diverse crops a year, sustaining massive populations and incredible ecological biodiversity. To wrap up our discussion, remember that the Indian monsoon is not a simple sea breeze. It is a highly complex system driven by the massive heating of the Tibetan Plateau and guided by powerful upper air jet streams. It is constantly modulated by global phenomena like El Niño and the Indian Ocean Dipole.
While its seasonal rains are the absolute bedrock of India's agriculture and economy, its delicate balance is increasingly being tested by human-induced climate change and landscape alteration. Understanding these interacting forces is essential for our future.